How's it going? Not great. No. Well, don't do anything that would break your mother's heart. How's everybody else? How's everybody else doing? I'm just going to grab the amplification because the other rooms I have this semester have like a much steeper bank, so I can literally get away with just shouting at people, but this one requires the amplification. So. The acoustics in this room are worse, shall we say. The hospital has great acoustics, but the computer system requires a Windows machine to be on in order for the AV system to work. So, yeah, it's terrible. It makes me sad. Particularly, it makes me sad when, like, they've got a great big press this button for help button on the podium, which they wouldn't need if it wasn't Windows. And when I pushed it the last time, it was like, there is currently nobody to take your call. Please call back again. And it's like, kind of defeats the purpose of the help button. Yeah. You're on your own, kid. You almost had to do it old school. Fortunately, that room still has chalkboards. Anyway, so the next few lectures are probably going to feel like something about programming. So that's a reference to YouTube videos. I'm going to have to get through some material pretty quickly in order to get us back on track for being on track with the course. So please pay attention. Don't fall asleep, because you might miss something important. So, right. So we were talking about dictionaries, right? This is our first programming example of an algorithm requiring a dictionary. We are performing, we are deriving a histogram from some set of data, right? So a histogram determines the frequency with which a particular element occurs inside of a set of elements, right? So essentially, it's not that difficult. You just loop through that set of elements, right? Adding things to a dictionary, adding numbers to a dictionary, depending on what you're finding in there, right? So, of course, we are not assuming anything is in the dictionary prior to us adding things to the dictionary, so we start off with a blank dictionary. Then, inside of the loop, we first test to see if the element that we are examining is inside of the dictionary or not, right? This is a very important step. If it's not in the dictionary, we need to initialize it. We initialize things, we add elements to a dictionary using an assignment statement. However, if the element already exists in the dictionary, we need to increment the existing value already stored in the dictionary, right? If we were to perform this operation, when the element has already been stored in the dictionary, we would just be overwriting that element with 1 each time, and we wouldn't actually be counting anything, right? And by the same we can't just start off here either. If D at C is not in the dictionary, then this would result in an error, right? Because we are asking to access an element from the dictionary that does not exist in it yet, right? So it's very similar to the x equals x plus 1, but you have to define x first type problem. Make sense? So, at the end of all that, you return D. Any questions? Good. So, we can also use loops to iterate over the keys of a dictionary. For loops are extremely handy. Please note that when you for loop over a dictionary, you are getting the keys, not the values. If it is your desire to for loop over the values of a dictionary, you must loop over enrollment.values. Right? The other way, of course, to get the values out is to simply access those values using the key which is generated by the for loop. Questions? Oh, yeah, that would help. Here I thought I was saving time. There we go. So, this slide is stupid and I'm skipping it. Right. Basically, if you want to do that as your own exercise, you have these situations. Which data type would you use? The decision is arbitrary in most of these cases. Any data structure can be used for any of these, but some of them are, more for one versus the other. Like the dictionaries, you can probably pick out pretty quickly, frequency of words in Alice's Adventures in Wonderland, for example. That would map words to frequencies, right? But, yeah, anyway. So, so let's talk about a problem. This is a real computing problem. This is a problem that's sort of in a class of problems which is relatively difficult, actually, deceptively difficult. Has anybody heard of NP completeness? All right, like 2 people. Boy, howdy, will you have heard of NP completeness by the end of your degree program? Yeah, without getting, let's talk about the problem. So, we are going to program an algorithm that computes change. Given a particular amount, a target amount that we're trying to create in change, we want to create an algorithm which computes a correct number of coins or bills that meets that target amount. This, you may, the more mathematically astute of you, you may instantly realize that this is an underdetermined problem, right? In algebraic terms, we have a series of variables multiplied by the denominations of each coin, right? So we would have, x, a times 5 plus b times 10 plus c times 25 plus d times 100 plus e times 200 is equal to 85. Solve for a, b, c, d, and e. Right? We do not yet have enough information to be able to deterministically solve this problem. There are many such arrangements of coins, as you might, you might put it elseways. So, for example, if our target amount is 185 cents, one possible configuration is 1 dime, 3 quarters, and 1 loonie, of course, in Canadian currency. Who's got another possible combination of coins? Class participation time. Yes?
1 loonie, 8 dimes, and 1 nickel.
1 loonie, 8 dimes, and a nickel. Yes, that would also work. We could do it entirely in nickels as well. Like there are lots of different combinations. Almost too many combinations. So, to this problem, we are introducing the additional constraint. We are not just interested in obtaining a coins, which equal the target sum. We are looking for the smallest number of coins equaling the target sum. This is this is something that's reasonably easy for a human being to figure out, but for a computer, it's actually it's more difficult than you might think. But anyway, so if we were to formulate this as a function in Python, we must be concerned with what our inputs are and what our outputs are. So we shall say our inputs to this function will be a tuple of coin denominations expressed as integers and a target value also expressed as an integer. Technically, these are unsigned integers, as it's not possible to have a negative target value. Our output will be a dictionary where the keys are the coin denominations and the values are the number of coins in the denomination. Make sense? So, who would like to propose an approach? Yes?
Try dividing the largest amount in first, and then go from there.
Precisely. Excellent idea. Let's try it out. One MP3. No, not those materials. 2022. Code. It is topic 4.5. There we go. So, define function, make change. This is a live coding session. I don't know why I feel the need to say that. If I'm programming, then it's a live coding session. I don't know. Some people put that like right on the slide, but that's, silly in my view. We should be able to figure out that if I'm coding, you should be coding. Anyway, so our inputs, a tuple containing coins and a target value. So, the first thing that we want to do is we want to set up the dictionary, right? We want a dictionary that has keys equal to the tuple of coin denominations, right? So, let's say, let's call it output. Started off with an empty dictionary. For coin in coins, output at coin is equal to 0. We are starting with the assumption that all of our coins, we aren't starting off making any decisions about how many coins are going in. At the end of this, of course, we're going to return output. Let's just test this to see that it's working. Test early, test often. Print, make change. Let's say we have a tuple of coin values 200, 100, 25, 10, 5, and I'm going to put the penny in just because I feel bad for it. We shall pass C and we shall pass T. And I'm going to fix that spelling error, which is being caused by numlock being on my D-pad, which is where my home and end keys are. Anyway, so there we go. New tab. Python 3, topic 4.py. Does that appear to be working? I would say so. So, Incidentally, there is a reason that I went from largest to smallest. It's because we want to iterate through the algorithm from largest to smallest. But if this was not the case, you could accept a coins tuple with arbitrarily placed coin values if you sort them first. This is one application of sorting algorithms. I'm going to assume the data is pre-sorted though. Seems like that's still pretty hard to see. I'm going to kill the lights a little bit more, yeah? Yeah. Better? Good? Okay. So, maybe I overdid it. Anyway. So, one logical approach to try to minimize the number of coins that we have here is to start off with the largest denomination, see how many will fit inside of the target amount, make that the number of coins, and then subtract that much from the target, and then move on to the next denomination. Right? Fairly straightforward. So let's do that. For coin in coins, right? Output at coin is equal to the target integer divided by the coin value. Right? Target is then equal to target modulo the coin value. Right? Anything else? Is there anything else needful? Let's see how it runs. So you can see that this algorithm has produced the intended result. We have 1 loonie 3/4 and 1 dime. Now, there's a slight optimization we might be able to do here. This target integer divided by coin will in fact result in 0 when the coin denomination is greater than the target. Therefore, we can actually just delete this initialization routine, at least in Python. Still works. Oh, wait, no, I need to save it. Save. There we go. Ta-da! You can also, if you want to do further optimization here, you can also put a subroutine, like you can put an if statement in that checks to see if target is 0 and breaks the loop if it's 0. You know, that's a thing you can do. But, you know, that works. Right? Any questions? Make sense? So let's see how we did in comparison to the slides. So this is the slide that describes the procedure that we just used. Take out as many of the biggest coin as we can until we can't take out any more. Da, 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 da. This is an example of a greedy algorithm. So greedy algorithms are a class of algorithms which take as much as they can at the step that they're currently at and then passes it to the next step. So this problem, has anybody heard of the Knapsack Problem? No?
I have.
You have? Oh, awesome. What's the Knapsack Problem?
So you have a knapsack.
Mm-hmm.
You want to go to the grocery store with.
Yes.
You wish to purchase goods.
Mm-hmm.
Different weights and different prices.
Yes.
You wish to find the most beneficial weight and price.
Yes. You want to be able to put the maximum amount of weight in your bag so that you only have to make it, you only have to make one trip, right? You want to pack your bag with as much value per unit weight as possible, right? This is a reformulation of the knapsack problem. The knapsack problem is something you guys are definitely going to talk about eventually in some class. So this is an example of a greedy algorithm. For each coin denomination, we are only concerned with the coin denomination we are examining, and we take as much of that as we can and then pass the problem on. Once we've passed the problem on, we are this is kind of a new way of thinking about problems, but this problem can be defined recursively, right? Once you make one decision about how many coins how many of the current coin you're going to compose in the target sum, you are then left with the same problem but smaller, right? You're left with a target amount and a number of coins, a number of coins, which, the number of coins you have to process has been reduced by 1. The target has possibly been reduced. Either way, you can apply the exact same algorithm, the exact same decision-making procedure to that smaller problem, right? This is algorithmic thinking, all right? You have to learn to think in recursions. So, let's see how we did versus how they did. First of all, we used a for loop instead of a while loop. Smart. They're using 5 lines of code where we're getting away with only 2. So, ours is bad. So here's the thing though, right? This will always find a set of coins that will make the target sum if one exists, right? Is it guaranteed to give the smallest number of coins? No. Interestingly enough. So, for example, let's come up with different C and T values, shall we? So let's say, just for the sake of interest, that we bought 1 additional coin in here. All right? Now let's say we want to make 14. Right? You can probably predict what's going to happen. First of all, what's the correct number of coins and which coin?
2 sevens.
2 sevens. What's the algorithm going to give us? A 10 and 4 ones. Right? So this greedy algorithm is not capable of always returning the smallest number of items, smallest number of coins. That is because this problem is difficult. Algorithmically difficult. Yes. Fact. The greedy algorithm gives the optimal result assuming that each coin is at least twice the value of the previous coin. Give me 1 second. If not, the change problem is hard in a very specific sense. It is NP hard. If you want to read up on this, there's a Wikipedia page on it. But essentially, it's impossible to solve for the smallest number of coins without some kind of backtracking procedure, right? You have to be able to make decisions, and as you're evaluating, see if you're on a good or a bad path of, possible decisions, right? Backtracking increases the complexity of this algorithm a lot. Basically, it means that each decision that's made in this algorithm you might need to go back on decisions, right? So rather than being just a straightforward path to the answer, this starts to look like something more like a binary tree, right? Or a decision tree. What NP-hard stands for is non-polynomial hard. That is to say, there does not exist a polynomial time algorithm which can solve this problem. Non-polynomial algorithms are particularly bad. Just because it's relevant, and this is the last slide of this thing, I'm going to pull up a slide from another course that I'm teaching this semester, just to give you the flavor for how bad a bad algorithm can get. Did I answer your question?
Oh, I was going to propose a potential algorithm to solve it, but
Wait till fourth year.
fair enough. It did involve backtracking though. So
Yeah.
what's its name?
In general, dynamic programming is the name for the class of algorithms which solve these most efficiently so far. So let's see here. Yeah, this is second year algorithms. So very long, yes. So general sketch. Once you start talking more mathematically rigorously about the runtimes of algorithms, you will find that they are proportional to the amount of items that go into it. So we are not concerned with the raw runtime of an algorithm. We are concerned with how quickly that runtime grows with respect to the number of inputs, right? So, you know, if you think about a searching algorithm, for example, if you're given an array of n numbers, you might search it in, 36n time, right? You can derive a timing function. We generally drop the constants and just examine the function, like the variable portions of the function themselves, in order to derive some kind of, rough categorization of algorithms for the purpose of comparing algorithms to other algorithms, right? So, when you hear me talk about linear algorithms, it means that the runtime is directly proportional to the number of inputs. If you hear me talk about a logarithmic algorithm, it's proportional to the logarithm of the number of inputs, right? So here's a bunch of algorithm big O functions, which, are possible. Linear, linearithmic, logarithmic isn't on this. Quadratic, cubic, 1.5 to the power of n, 2 to the power of n, and factorial, right? When we are talking about the make-change problem, I believe we're talking about this category because each decision is a variable number of coins, right? When you decide how many quarters should go in there, you could decide 1, you could decide 2, you could decide 3, you could decide 4, right? So the number of possible solutions from which you have to select the correct solution is proportional to the number of permutations of different coins you can choose, right? So, boop, right? Which is why the greedy algorithm, although it's not guaranteed to give you the best result, will give you a result, and that's preferable to no result. So, if n is 1 million, a linear, assuming we can process, what is it, a billion? A million? Yeah, so we're performing a million, exactly 1 second. We're processing a million n's a second, right? In linear time, that takes 1 second. Linearithmic, that takes 20 seconds. Cubic, that takes 12 days, right? jump up a bit. That'll process 1,000 in 1 second. Cubic will process 1,000 in 18 minutes. You can see that these numbers grow very, very large very quickly. We cannot process 30 items in less, at maximum, it will take 10 to the 25 years to process 30 items with a factorial runtime, right? And you can judge by the fact that they went to the trouble of saying 10 to the 25 here, that very long is very long indeed. Just for the sake of comparison, the order of magnitude of the age of the universe so far, I believe, is 10 to the 7. So 10 to the 25 years is like, if you took the universe, right? Assuming the universe is a simulation, right? Which, some people might not think, assumption, really? But assuming that the universe is a simulation, we press the pause button right now, and we rerun the universe simulation for every, picosecond that has happened in the universe so far, and then we do that process a few more times. That's the order of magnitude that we're talking about with numbers of this scale, right? So, bad algorithms can be so bad that they take much longer than the age of the universe so far to execute. And of course, it's unlikely the hardware is going to last that long. So, theoretically possible, but not practically possible. Right? Make sense? Cool. So, anyway, so that's just a little look into things. You get similar levels of computational complexity in 3 integers. So, yeah, this is generally a problem known as the state explosion problem. It would be really nice to be able to solve the state explosion problem, but the fact that NP-hard problems are NP-hard is what makes recursion, or that's what makes encryption work. So if somebody did find a solution to solving NP-hard problems in polynomial time, they would be able to break all existing encryption almost instantaneously, and that's probably a bad thing, Basically, all computer security in the world is based on this idea that it would take you longer than the age of the universe to guess the correct answer, right? So, anyway, heuristics though, you gotta watch those heuristics. So, moving swiftly on, we now talk about topic 5. We're going to talk about functions in somewhat more depth. We're also going to talk about recursion in somewhat more depth, quite a bit more depth actually. So let's get on with it. Functions are a way of grouping together a sequence of operations under a common name so that it may be referred to multiple times later. They're sometimes called subroutines. Everybody know what a function is? Give me a thumbs up if you know what a function is. Anybody not know what a function is by this point, having already done 2 assignments where you should know what a function is? Okay, well then I think we can dispense with the pleasantries, shall we? Syntax of functions, you should already know this. So, here's an important piece of nomenclature. The function parameters, or arguments, which are provided in the function declaration themselves, those are called formal parameters. The values which are passed into the function when the function is invoked are known as actual parameters. All right? When a function is defined, the formal parameters are included in the function definition. When the function is invoked, the actual parameters are provided. During invocation, the formal parameters are bound to the actual parameters using assignment in the regular sense. Python uses pass by assignment. Python passes by assignment, in which each formal parameter, there's the trick, by the way, for reading stuff that's off the page. Python uses a pass by assignment in which each formal parameter is assigned using the equal sign operator to the actual parameter, which is something I just said. So here's a clever little trick. And this might be like news to you, actually. In Python, we have the ability to assign default values to parameters. If you put a little equal sign inside of the function declaration line itself and put a literal there, what you're doing is you're turning that into an optional parameter, right? You may either call the function with that parameter or not. In this particular case, we're defining some kind of sorting algorithm that we don't actually care to define. The optional parameter determines whether we're sorting by ascending or descending order, right? When we invoke this function, we may do so in a number of different ways. We may leave out the optional parameter, in which case the default value is used. We may provide, of course, a value for that default parameter in place, but some functions have quite a few default parameters. If you don't want to get at it positionally, you can use the name of the parameter and perform an assignment statement to that parameter inside of the function call itself. Right? So, an example of this which I like is the print function. So, Python 3, help, print. So this is the help information for print. Incidentally, just so you know, if you have access to a Python interpreter, you also have access to the Python documentation. Just call help, use the help function, provide the name of the function you want help on. All right? It'll tell you what the parameters are, description of the function. You do have to know the function's name. But this is permitted aid on the test. All right? So, you'll notice print has a number of optional parameters. Separator, space, end, new line, right? File, system.stdout, flush is false, right? Let's say, just for the sake of argument, you wanted to just change the ending parameter, right? So, normally it just inserts a single new line, but if we print help, I'm trapped in a command prompt, and then we say end is equal to new line, new line, new line, put, something in there. Right? Make sense? By default, Python inserts a separator, which allows you to put multiple things in there. You can make your separator a tab. Then you can add 1, 2, 3. And it inserts tab characters between them. Make sense? Notice that and like this is the inverse of the order in which those optional arguments appeared inside of the printf definition. Also notice that because of the nature of printf, or print, I know I'm saying printf because that's the C version that this thing's calling under the hood, but man. Because print supports an optional number of arguments, right? We can provide as many arguments to print as we like, in fact. There's no way to get to n except by specifying it, right? Because if you just put new line, happy face, new line here without specifying n equals, it would just print it like it was one of these guys. Make sense? I mean, since it's end, it's effectively doing that anyway, but... Any questions? Yes?
So the Python print method can print a string, but it can also print like lists and dictionaries. So
Yeah.
that print would be like an overloaded method, right?
You want to know how it actually works? We're going to see how it works later on, right? But so Python's object-oriented, right?
Yeah.
Everything is a class. Python, they call them magic methods in Python, but what it essentially is you can overload basically all of the default operations and operators. You can overload them within the class. So if you overload the string conversion method, then that allows you to define what printing as a string means for that particular class. So like that's where the square braces are inserted for lists and that sort of thing. And you can define it for your own custom classes as well. Make sense? And you can overload anything. You can overload like plus, minus, integer conversion, whatever you want. Equality, Question?
Isn't it disturbed different from when it's printed? If you call string on a list, it'll just join all the elements together. But if you print the list, it'll show the elements. Isn't that like wrapper, I think? For when it's printed to the console instead of when you just call string on it?
Let's see. So if I have a list, and assuming it's like just a regular list of numbers,
Try a list of strings maybe? Not sure. Maybe it's number.
nope. Curiosity satisfied? Cool. Yeah, this str function is in fact the same function that's used by print. So the way this works is the way that printing stuff off works. Yes. Any other questions? Okay. Good. So let's talk scoping. How many people are familiar with the concept of scoping? How many people are not familiar with the concept of scoping? All right, good. Something new for you guys, at least half the class. So, there are more complicated reasons that this is the case. But I'm going to have to ask you to wait till you take 1xc3 with me. Hopefully I get to teach it this winter. In order for you guys to sort of explore the function called stack and why local variables are really only the most local variables. But our sort of intro to programming first pass approximation of how things bloody work. You've got local variables and you've got global variables. All right? Local variables are local to the function in which they exist, right? When a function starts up, all of the variables that it declares are contained within that function's stack frame, which is something that doesn't really make sense unless you look at it from the perspective of Python Tutor. I'm just going to open Python Tutor now. Python Tutor. There we go. I've shown you guys Python Tutor yet. Have I? Have I not shown you this? Oh, shoot. Sorry, I should have. So Python Tutor is a debugging tool which allows you to visualize data in a very intuitive sense. It's got a reasonably small hard cap on the size of the program that you can feed into it, but it should be good for most of your assignment questions. So let's just say define function f takes x and y, sure, z is equal to x times y, return z, something reasonably simple. Let's say a is equal to 9, b is equal to 3, print f at a comma b. All right? So it lets you step through your program line by line and see how it affects memory. So you'll notice that the first thing that gets created is the global frame. The definition of f, the function, is placed into the global frame. It's a function, so global has access to this function. It's inside of the global frame. Global is the same thing as main here. When we declare the variable a, it is also placed in the global frame. That makes it a global variable. B, similarly, is a global variable. When we print f at ab, we are invoking f. This is what happens. A new stack frame is created. All right? The formal parameters of that function have been assigned the input parameters given, or the actual parameters given in the thing that's called it. Right? So, we have x being 9, y being 3. Right? We then assign z x times y, so we create a new variable. Note that it has been placed inside of the stack frame for f. Right? What happens when f returns the value? It calculates its return value as 27. It puts that and prints it to the display. But note that the stack frame, which contained all of the variables that f was using, has been deleted. So, the local variable, I've just got one thing before we go. Let me finish this thought. All right? The variable z no longer exists. Right? If we try to access it from the global frame, after this function has been terminated, it results in a name error. Name z is not defined. Because it isn't. Because where is it? It's nowhere here. Cool? Any questions? Yes? Can you say that a little louder? No, this is not going to be covered on this test. It will be covered on the next one.